All right, guys. In this video, like I said, this is gonna be the last part, the last chi-square test that we're looking at. So you guys are gonna be watching this, and then we'll kind of just wrap it up everything on Friday, and then we'll kind of start chapter 12. So here's a chi-square test for independence. And just while as you're thinking about this at the beginning, just think about what does it mean for independence, and that leads directly into this first question of what does it mean for two variables to have an association? And what does it mean for two variables to be independent, and how do you state the hypotheses? So if you think about it, the probability independence means that the probability of one does not have an impact on the probability of another. So if two variables associated, right, that means they're going to impact each other. Independent means they're not. So if you think back to chapter 4, chapter 5, when we talked about probability, we kind of talked about flipping a coin, right? And flipping a coin, we said that those are independent because if you flip a coin once, it's not going to impact the likelihood of getting ahead on the second flip, right? So those are called independent. And so if they do impact one another, they have an association. And so again, think back to chapter 5 with independence and conditional probabilities. So that leads to what are our hypotheses going to be? Well, we have HO, which is where there's no association. That's kind of your baseline, right? And then if you think about it, you have HA, which is there is an association. Okay, so how are tests of independence different than tests of homogeneity? So here, okay, both of them, so test of homogeneity, that's what we're looking at last week. So both start with a two-way table. And if there is one sample and two variables, we are testing for an association. If there are two or more samples with only one variable, we are testing for homogeneity. Okay, which kind of makes sense because if you think about it, homogeneity, homo being one, so we have one variable. But here we want to test an association between multiple variables. Okay, and this is really just a question of how did we get our data. That's kind of what the idea is how did we get our data. So once you read these questions to determine if it's a test of homogeneity versus a test of independence, you got to look for how many variables do we have, how many samples do we have. Okay. So how do you calculate the expected counts for test of independence? So to find the expected counts, I'm just going to write EX. That's going to be equal to row total. So row total times your column total divided by the whole table total. Divided by table total. Okay. And remember, you got to find this for each cell. So for each cell, and remember our chi-square stat, this is all going to stay the same, is equal to observed, or sorry, I forgot the sum of the observed minus expect, this all stays the same. So I'm going to O minus E squared divided by E. And so what are the conditions? Okay, all the conditions are the same. So we've talked about this before. We had one, which was random. 2, n needs to be less than or equal to 1/10 of big N. And then we had expected counts bigger than 5. So a lot of this stays the same, right? The expected counts changes a little bit. Your degrees of freedom is going to be rows -1 times column -1. So that stays the same as well. So I'll put it over here in a different color so it stands out. So df equals row -1 times columns -1. So the number of rows -1 times the number of columns -1. Okay. So if you look at this first example, and I want you to practice your HO versus HA. I'll let you do that, right? Again, you're just testing for, is there an association between these things? And then is there not an association between these things? And so the biggest thing I want to spend time on is looking at, okay, how do you calculate the expected counts? So I'm going to label these columns. So here's 1, here's 2. Okay, so for the first column, all right, so in this first cell, I'm going to highlight it. I'm going to kind of focus on that one for right now. So I'm going to highlight it. So in this first cell right here, to find that expected count, you do row total, so 158. So again, if I'm looking in this column here that I've got kind of highlighted, look at the row total, so which is 158, which is right here. Column total, which is, oh, not that number, sorry, 227. Divided by the grand total, which is 460. And that gives you a value of 77.9696. Okay, remember, we don't round these numbers because these are expected counts. And then you can do the same thing for the next one, right? So then you go to the next cell, okay? And so now I'm looking in this row in the same column. So then you do the same thing. So then you have 86 times 227 divided by 460. And that gives you a value of 42.4391. The next one, I'm not going to write out all the work. The next one's going to be 106.591. And then in the second one, when you look at, so if I'm starting here at 73, I'll write out the first one. You have 158, that's there. 233, that's on the bottom. So that's in the row, 233. And then divided by the total, which is 460. And that gives you a value of 80.03. And if you keep following that pattern, or you keep doing that for each of the cells, the next one should be 43.5609. And the last one should be 104.713. So those are all your expected counts. And so then once you have all those values, all right, you can go in and then calculate your chi-square. So then your chi-square is equal to the first one, which is 85, minus the expected count from the first one, which was 77.9696, all squared, divided by the expected count, which is 77.9696, plus, and then you go to the next one. And then you keep going along, so then you have 42 minus 42.4391, all squared, divided by 42.4391. Again, observed, expected, and then expected on the bottom as well. Okay. You keep doing that all the way across. Do that for all the cells. You get a chi-square of 2.5765. And remember, when we talk about this, the reason why we want to do this by hand is because when you get to the follow-up, right, it's easier to say which ones have the biggest impact, right? So for example, the second one here, you're going to have a decimal square divided by 42, okay, which is going to be a really small number. So this second cell here, which refers to females with the same length finger, okay, it's going to be a really small, it only contributes a tiny bit to your overall chi-square, so this one doesn't have a major impact. Okay. And so then degrees of freedom, row -1, columns -1, so you have 3 minus 1 times 2 minus 1, so degrees of freedom equals 2. And this gives you a p-value of 0.0356. Okay, this is less than alpha. Or sorry, not 0.03, 0.3. Sorry, 0.3. 0.356. So this is greater than alpha. And because it's greater than alpha, we fail to reject. And so because we fail to reject HO, what it says is there's no association between gender and finger length. Okay, so the whole interpretation, the reason why we do all this is again to determine if HO is true or is H1 true. And we just basically say that there is no association between gender and finger length. Moving along. So here, if you read this problem, so if you look at this, we have multiple variables and multiple populations. Okay, so then it's like, okay, well, what kind of test should we use? And so for part A, basically the whole idea is that because there are two variables or two or more populations, right, a goodness of fit is not appropriate. So remember, goodness of fit, so for part A, goodness of fit only works for one variable. So part A, your hint to yourself is goodness of fit is only one variable. Okay. So then now the next question, describe how the data could have been collected so that a test of homogeneity is appropriate. So here, you would have to do 6 independent samples, and then 1 from each category. And then you have to ask whether each person uses social media or not. Or we could take 2 independent random samples, 1 of each social media or social network users, and 1 of people who do not use and people who do not use social media or social networks, and ask every member of each population how old they are. So you can kind of take 1 from each group, right, whether they use social media or social networks or not, and then select 1 person from each group. And for part C, how do we use tests of independence? We would take 1 random sample from the population and ask every member about their age and whether or not they use social media or social networks. This seems like the most reasonable method for collecting data. So test of association or independence is probably the best choice. The thing is that we don't know for sure until we know how the data was collected. So for part D, this is the big one. In general, how do you tell the difference between independence and homogeneity? So I'm going to write down part D, it's the big part. So in homogeneity, we have 1 set of totals. Your marginal distribution. Chosen by the researcher. In independence, both sets of totals are random. So when you use chi-squares, again, the biggest thing is to think about how the data is collected and how many groups you have and how many variables you have. And that's going to be the big thing. So thanks for taking time to watch this video, guys. We'll kind of summarize a lot of this. We'll talk about this page a little bit more in detail in class because you guys can ask questions because it's kind of an important page. But hopefully you guys got some notes taken down, and then we'll kind of go over this, and then we'll start chapter 12 on Friday. So have a great rest of your day.